To the lesson 25 demo for college algebra. I'm talking about rational functions today. Rational function is a ratio, the root word of rational is ratio, of two polynomial functions. So that is, a rational function is a function that can be expressed in the form p of x over q of x, where p and q are both polynomial functions and q of x can't be 0 because it's in the denominator. So this is an example of a rational function. The domain of a rational function is the set of all real numbers except any x values that will make the denominator 0. So for this rational function here, any x values that would make the denominator 0 would be x values to exclude, and that would be x equals 0, 4, and -2. Right? So my domain is all real numbers except for 0, 4, and -2. So I could write that in set builder notation, set of all x's such that x is not 0, 4, or -2. Or I could write it in interval notation by starting with -∞ and moving to the right until I hit the smallest excluded value, which is -2. Don't include it, so you put a round bracket. Then union that with -2 to the next smallest excluded value, 0. Don't include the 0. Union that with 0 to the next excluded value, 4. Don't include the 4. And then union that with 4 to infinity. So that's how you would use interval notation to exclude those 3 values. All right, let's think about what happens near a value that is excluded from the function's domain. Oops. So I'm going to start with a simple polynomial function. It's called the reciprocal function, f of x equals 1 over x. What value is excluded from its domain? 0. You can't put x equals 0 in. Maybe I'll write that specifically. X can't be 0. So I'm going to fill in this table of values to see what happens to the y values as the x values get close to 0. So if I put in 1, f of x equals 1 over x, f of 1 would be 1 over 1, which is 1. And if I put in a half, a little bit closer to 0, I get 1 over 1/2, which simplifies to 2. Plug in a tenth, 1 over 0.1. You could put that in your calculator, or you could say how many times does a tenth fit into 1? 10 times. 1 over 0.01 is 100. And 1 over 0.001 is 1,000. So it seems like as I plug in smaller and smaller x values, 1, a half, a tenth, a hundredth, a thousandth, as I plug those into the reciprocal function, my y values get bigger, 1, 2, 10, 100, 1,000. So I would say that as the x values approach 0 from the right, meaning that all these x values I was plugging in were positive, right? Then the values of f of x, the y values, approach infinity. They just get bigger and bigger and bigger. So the shorthand for that sentence would be, as x approaches 0, the little plus sign means from the right, f of x approaches infinity. So let's see what happens if we approach 0 from the left. Okay, so from the left side of 0 on the number line. So I'm going to plug in negative values that get closer and closer to 0. So if I put in a -1, 1 over -1 is -1. 1 over -1/2 is -2. 1 over -0.1 is -10. -100, -1,000. As the x values approach 0 from the left, the values of f of x approach -infinity. They're getting bigger and bigger and bigger in the negative direction. So this is my shorthand for that sentence. As x approaches 0, this little negative sign up here means from the left. F of x approaches -infinity. So that means that as I approach 0 from either side, the function blows up or blows down, and we call that a vertical asymptote at the excluded value of x equals 0. It's being annoying. All right, so we know what happens near x equals 0. We want to investigate some other characteristics of the graph. So does it have any x or y intercepts? So x-intercepts happen when the function equals 0. Does 1 over x equal 0? This is to find x-intercepts. Well, you'd have to multiply both sides by x to solve this, and you would get 1 equals 0, which is impossible. So there are no x-intercepts, therefore none. And then y-intercepts, those happen at f of 0, which would be 1 over 0, which again is not undefined. So there's none, no x or y intercepts. All right, let's think about the end behavior. What happens at the far right and the far left ends of the graph? So I'm going to plug in bigger and bigger x values. So I'm going to the right. What is the end behavior as x approaches infinity? So 1 over 1 is 1. 1 over 10 is 0.1. 1 over 100 is 0.01. And 1 over 1,000 is 0.001. So as x approaches infinity, it looks like f of x is approaching 0, getting really, really small. And then I'm going to approach negative infinity as x approaches negative infinity. So 1 over -1 is -1, negative 0.1, negative 0.01, negative 0.001, also approaching 0, right, just from the other direction. Y values are approaching 0 from below 0. So we call this a horizontal asymptote at the line y equals 0 or the x-axis, because my y values are approaching 0. All right, so we're going to put this all together and sketch a graph of the reciprocal function. So I know I have a vertical asymptote at x equals 0. So I'm going to draw my asymptotes as dashed lines. And I have a horizontal asymptote, y equals 0. Okay. And then 1 over x. So 1 over 1, that was 1. And then this is going to come down. Comes down towards 0. That's my end behavior. And this blows up. When you approach 0 from the right, my y values go to infinity. And then I have -1, -1. And as I approach negative infinity, my function approaches 0 from below. And then as I approach 0 from the left, this goes down to negative infinity. This is a new parent function to add to your list. And what kind of symmetry does it have? Odd / origin, right? It's an odd function. It has origin symmetry, which means that if you were to fold it over the x-axis and then the y-axis, then the two pieces line up. So just to show f of -x, confirm that we have this kind of symmetry, that would be 1 over -x, which is the same thing as -1 over x, which is negative f of x. So if you put a negative in, you get the negative out. Opposite x's give opposite y's. So this is odd or origin symmetry.